Now let's go to Hypercube. So for the Hypercube, we discussed one algorithm, and the time analysis of that was TS plus TWM times log P. And what is a good lower bound for Hypercube? So I hope you remember what is an Alltoall operation, right? So what is an Alltoall operation? Let's quickly recap that. Alltoall. Let's say you have some data on rank 0, you have some data on rank 1. So this is, let's say, A0, this is B0, B1, 2 and BP minus 1, right? A1, B1, B2, A2, right? And so on, right, up to P minus 1. And what do you want to do? If you consider this to be a matrix spread across P minus 1 nodes, it's nothing but the transpose of this matrix, right? So at the end, you want rank 0 to have the data A0, B0, C0 and so on for all the P minus 1 nodes, right? So that's nothing but the first row over here. This becomes the first column, right? And what will be there on rank 1? A1, B1 and so on, right? Okay, that was Alltoall, if you recall. Alright, so we are considering that the entire array on each node, let's say that is of length m, right? So what's the lower bound? Can you give me any lower bound for Alltoall? What is the minimum time it will take? If I'm talking about large messages, so ignore the TS term, let's only concentrate on the TW term, right? So what's a good lower bound? Same as what we discussed last time, you can at least start with that, right? So what does rank 0 need to do? Well, it needs to send out all this data, right? It needs to send out all this data. So it will at least have to send out, so we are assuming this entire array is of size m, right? So m by p times p minus 1. Yeah? That's a lower bound. It will have to at least transmit this much data. Otherwise, you can't perform an Alltoall, right? So it takes this much time to at least send out all this data, right? If you want to send all of this data out of node 0, it's going to take at least this much time, right? So that's roughly about what? That's roughly about MTW, right? So what is an algorithm? So we want to obtain an algorithm that matches this lower bound. So what is the algorithm I currently have? It's TWM times log P. I want to somehow get rid of this log P, right? Because my lower bound is TW times M. Yeah, so the question is, how do I get rid of this log P? So here is an algorithm. In each iteration, every node exchanges means sends and receives, sends and receives data from one other node. Okay, how many iterations are there going to be? Well, in the first iteration, node 0 is going to send and receive data from one other node. In iteration 2, it's going to send and receive data from one other node. When we are talking about sending and receiving data, we are talking about those m by p elements, right? This was the matrix, right? This was rank 0, 1, 2, 3, 4 and so on, right? So this is the data that it's supposed to send here, and this is the data that it's supposed to send here, right? So what I'm saying is, in one iteration, if I say that 0 and 1 are exchanging, what does that mean? That means that 0 will send to 1 the part that 0 has, which is finally supposed to go to 1, and 1 will send to 0 the part that is supposed to reside with 0 at the end. Okay? So it's clear what we are doing in each iteration? we are exchanging m by p elements with the respective node. Okay. Now tell me, how many iterations will there be? In each iteration, I am exchanging data with one other node. So how many iterations will there be?
M by p into p minus 1 twice. Either the
number of iterations. So in one iteration, I am exchanging m by p data. So yeah, come again.
M by p into p minus 1. 2 times.
No. Why is m coming into the picture? M shouldn't come into the picture.
There are,
you are exchanging m by p data. So essentially, you are exchanging all the data that is supposed to go to 1. In the second iteration, maybe it will exchange all data which is supposed to go with node 2. So how many iterations will there be? P minus 1, right? So there will be p minus 1 iterations. Okay? So let me just first write down the algorithm, right? And then we'll discuss how it works. For j is equal to 1 to p minus 1, this is the iterations. Node I exchanges data with node I XOR j for all I. So every node will exchange data with node I XOR j. Okay? So first let's understand that this will exchange data with all the nodes, right? So let's say you have node 0, 1, 2, 3, 4, 5. Let's take a smaller case. Let's just take the case of 4 nodes. Yeah? So in the first iteration, what will happen? Well, iteration number is 1, j is equal to 1. So 0 will exchange data with 0 XOR 1. 1 will exchange data with 1 XOR 1. 2 will exchange data with 2 XOR 1. 3 will exchange data with 3 XOR 1. What is this? What is 0 XOR 1? 1. 1 XOR 1, 0. Right? So essentially what is happening in the first iteration? Well, 0 and 1 are exchanging data. That's what's happening in both ways, right? So essentially 0 sends to 1 and 1 sends to 0, right? 2 will send data to 2 XOR 1. What is 2 XOR 1? What is the bit representation for 2? 1, 0. What is the bit representation for 1? 0, 1. So what is the XOR? 1, 1. Yeah? So 2 is sending data to 3 and 3 is sending data to 2 because 3 XOR 1 is 2. Okay? So in the first iteration, 0 has exchanged data with 1 and 2 has exchanged data with 3. Okay? What will happen in the second iteration? Well, now j is equal to 2, right? So this will exchange data with 0 XOR 2, 1 XOR 2, 2 XOR 2, 3 XOR 2, right? What is 0 XOR 2? That's 2. What is 1 XOR 2? That's 3. What is 2 XOR 2? 0. And what is 3 XOR 2? 1. Yeah? So you have to convince yourself that the XOR that you get when you run numbers from 1 to p minus 1, in every iteration, the XOR of your node ID and j will result in a new node, right? All these nodes are distinct, right? Well, in this iteration, 0 has exchanged data with 2 and 1 has exchanged data with 3. And in the third iteration, you are going to XOR with 3, so 0 XOR 3, 1 XOR 3, 2 XOR 3, 3 XOR 3, right? So this is 3, this is 0, this is 2, this is 1, right? So essentially what have you done? 0 has exchanged data with 3 and 1 has exchanged data with 2. Well, all the pairs have exchanged data with each other and therefore the all-to-all is complete. The transpose is complete, right? Okay? So this is the algorithm. But now what is the critical part? So there are p minus 1 iterations. What is the cost? Let's analyze the cost. The cost is ts plus how much data am I sending? M by p, right? Times tw. Yeah, that's the cost, provided the paths for each pair that are communicating are disjoint. There is no congestion. provided there is no congestion. Okay, that means that 0 has to send to 1 and 2 has to send to 3, right? This is actually very simple in 2 dimensions, so we won't see too much of an issue, but you have to realize that as you go to higher dimensions, it will become more complicated, right? So 0, 1, 2, 3, right? So 0 sends to 1 and 2 sends to 3. So clearly the links that they are using are disjoint. So all this communication can happen together. 0 can send to 1, 1 can send to 0, 2 can send to 3, 3 can send to 2 without any issues because no links are being shared, right? This is what the cost will be, what we have decided, right? Now in the second iteration, 0 communicates with 2, 1 communicates with 3, sure, right? Again, I can see that they're disjoint. The third case, you have to be a little more careful, right? What is the third case? The third case is that 0 communicates with 3 and 1 communicates with 2. You have to make sure that no link is being used twice, right? So how does 0 communicate with 3? Right, on this path. So let's say that 3 sends to 0 along this path. Okay. Now simultaneously in this iteration 1 has to communicate with 2. How is 1 going to communicate with 2? Can you tell me a path where 1 can communicate with 2 without conflicting with any links that are being used by 0 and 3 together? Can it? No, because well, if I look at 1, 1 has to send to 2. 1 has only 2 links going out towards 3 and towards 0, but both those links are being used by the communication between 0 and 3. So I have a problem, right? Then this analysis is not true anymore, Ts plus m by p tw in this iteration, right? It will take more time because that link is being used by twice the data. Okay, so getting the problem? Okay, so what is the solution to this? Let's look at the solution. Well, 0 communicates to 3. Let 3 communicate with 0 along this path. What does that mean? We are always going clockwise. Yeah? 0 goes to 3 clockwise, 3 goes to 0 clockwise. Now 1 to 2 can communicate anti-clockwise, right? So 1 can send to 2 along this path and 2 can send to 1 along this path. And now I have a conflict-free routing. Okay? Alright, now this problem becomes more concerning when you go to higher dimensions. It's a little more complicated. Now you've got to figure out in 3 dimensions and 4 dimensions, right? Hypercube, log p dimensions. So how do you do that? So this routing is called E-cube routing. Okay, it's very important. It's called E-cube routing in hypercubes. Okay. So the way it works is that, so let's talk about iteration j. Right? So 0, 1, 2, 3, 4, 5, 6, 7. These are the 7 nodes which want to communicate, right? And let's say that j is 5, right? I'll just take some number. I'm not taking the extreme values because those are simpler, right? So let me just assume j is 5. So we are in the 5th iteration. So let's just look at what is the communication. So we won't go through all the iterations, right? One iteration is enough. So in the 5th iteration, what will happen? 0 will communicate with 5, 5 will communicate with 0, yeah. What will 1 communicate with? Well, 0, 0, 1, 1, 0, 1, what is the XOR? 1, 0, 0, yeah. So 1 will communicate with 4, 4 will communicate with 1, what about 2? 0, 1, 0 with 1, 0, 1, 1, 1, 1. So 2 will communicate with 7, 7 will communicate with 2, and 3, 0, 1, 1 with 1, 0, 1, right? So 1, 1, 0, that is 6. Well, those are the only 2 left. 3 with 6 and 6 with 3, right? So how does E-cube routing work? Well, this is the way E-cube routing works. Examine j, write it in bit format, right? So j is 1, 0, 1. There is a dimension associated with every bit, right? Convince yourself of that. What is that? What is that dimension? 0, 1, 2, 3, 4, 5, 6, 7. That is the dimension in which that particular bit differs. So remember, every node has log p adjacent nodes, each of them differing in one of those log p bits, right? Each node is numbered using log p bits, and along each dimension there is one bit that changes, right? That is the dimension corresponding to that bit. Is that clear? So if you look at it, the rightmost, let's call that the first bit, that will be this dimension, 0, 1. Look at any node, right? It is this horizontal direction where the bit differs for the adjacent node, right? That's the dimension corresponding to this. What is the dimension corresponding to this bit, the second bit? That is where the second bit differs. What is that? Well, that is this dimension, right? Look at any node, 0, 2, 1, 3, 5, 7, 4, 6. They are all different in the second bit. And similarly, this corresponds to this dimension, the upward downward direction, right? Again, you can check, right? All these nodes differ in exactly the third bit from the right. Okay, so how do you do E-cube routing? Well, what I'm going to do is the following, that in the first iteration, I am going to communicate along the first dimension. In the second iteration, I'm going to communicate along the second dimension. In the third iteration, along the third dimension, right? So in the case of 5, what am I going to do in the first iteration? So I have to send to a node which differs from me in the first bit and the third bit. So in the first iteration, I will send along the direction of the first bit. So let's examine what will actually happen, right? Let me just remove these and let's just examine what will happen. Let's see how 0 sends data to 5. In the first iteration, where will it send the data? It will send the data to 1, because that is the bit that differs, right? 0 will send to 1, 1 will send to 0, 2 will send to 3, 3 will send to 2, 4 will send to 5, 5 will send to 4, 6 will send to 7, 7 will send to 6. That's what happens in the first iteration. Everybody has sent data to the node which differs in the first bit. Second iteration. Well, second iteration, now I'm supposed to communicate along the second dimension if required. Well, here the bit is 0. That means I'm not even supposed to transmit along the second dimension, right? So I don't need to actually do this phase, right? I can get rid of this iteration. Third iteration. Well, this is a 1. So now I'm going to transmit along the third dimension. Let's see what happens. So let's examine the data going from 0 to 5. Well, in the first iteration, it went from 0 to 1. In the second iteration, it's going to go from 1 to 5. So it's reached the destination. Simultaneously, what happens to the data coming from 5 to 0? Well, that went from 5 to 4 in the first iteration. In the second iteration, it will go from 4 to 0. Is it clear?
So when one is sending data to 5, at the same time 5 is also sending the data to 1.
Hold on. 5 will send data to 1, but that's for a different communication, right? So far, we have looked at 0 to 5 and 5 to 0. 0 was sending data to 5. In the first iteration, that data had reached 1. In the next iteration, this is this very data, right? This data is being forwarded now on the link from 1 to 5. Okay? And this data which 5 had sent to 4 is now forwarded to 0. Remember, 5 is not communicating with 4. 5 is communicating with 0 in this iteration. Endpoint for this data is node 0. Okay? So we've looked at this, we've looked at this. Okay, let's look at one other. So the question you asked, right? 4 is sending data to 1. What happened to that data in the first iteration? The data that 4 was sending to 1. In the first iteration, that data 4 sent to 5. In the second iteration, 5 will forward it to 1. The second iteration is just a forwarding phase. It's not new data that is being sent, right? The same links are going to be used in both directions, but the point is they are being used for different data altogether. Okay? Similarly, I mean, if you look at 0, 4, one other communication will be using 0, 4 in the downward direction. Which is that communication? That is what 0 currently has. 0 has the data which was forwarded by 1. So that means it must be the data that must have originated from 1. So it's the data from 1 to 4. In the first iteration, 1 had sent it to 0. In the second iteration or third iteration, whatever you want to call it, depending on whether you're including the 0 bit or not, no communication happens in that iteration. Okay. In the second iteration, this data that 1 had sent to 0, which was destined for 4, is going to be forwarded by 0 to 4. Yeah. In each iteration, all the data that is being forwarded is using separate links. Right? This is called E-cube routing. So I gave you a simplistic view of E-cube routing in 2 dimensions with 4 nodes. So you extend that to higher dimensions, and that essentially is your algorithm. So then this cost holds, right? So let's just revisit the cost again. There are p-1 iterations. In each iteration, I can say that this is the cost if there is no conflict of links. And I have just shown that using E-cube routing, there is no conflict of links. Right? Therefore, this is the cost. right? So let's go back to our chart. So what is the algorithm I have? I have p minus 1 times ts plus m by p tw, right? That's the new algorithm I have, and now that matches the lower bound. Okay. Alright, so I have lower bounds for almost everything now, right? I have lower bounds for all reduce, I have lower bounds for all to all. Well, architecture dependent, but that's fine. At least I should know that I'm able to achieve some lower bound, right?